Prove that 5 plus root 3 is an irrational number. To solve this, we can use the method of contradiction. We will start with the assumption that 5 plus root 3 is a rational number, and therefore we can write 5 plus root 3 as p by q, where p and q are integers and q is not equal to 0. So we can rearrange as 5 minus p by q is equal to root 3, and I can do some simple modifications. It will become 5q minus p whole divided by q is equal to root 3. But we know that p and q are integers, so definitely 5q minus p by q, this will definitely be an rational number. But on the other side we have root 3, which we definitely know is a irrational number. On the left hand side we have a number 5q minus p by q, and this p and q are integers, and therefore 5q minus p by q, it will definitely be a rational number. On the right hand side we have root 3, okay, and we know that root 3 is an irrational number, and therefore it goes against our initial assumption that 5 plus root 3 is rational, or simply the answer is that 5 plus root 3 is a irrational number. Prove that root 11 plus root 17 is irrational. So let us assume that root 11 plus root 17 is a rational number. So we can write root 11 plus root 17 is equal to p by q, where p and q are integers and they are in the smallest form, okay. So I can rearrange this as root 17 minus p by q is equal to minus root 11, okay. Now what I do is that I square both the sides. So I'm going to square this side and I'm going to square this side. Now I can write 17 plus p square minus q square minus 2 root 17 p by q is equal to 11, or I will isolate this root 17, okay. So I can write 6 plus p square by q square is equal to 2 root 17 p by q. In other words, this is going to be 6 q square plus p square divided by 2 pq equal to root 17. Now we know that root 17 is definitely going to be a irrational number. Why? Because this is square root of a prime number. For any prime number p, root p will be a irrational number. And on the left hand side we have a term using p and q, and we started this problem with the assumption that p and q are integers. So this is definitely going to be a rational number, but on the right hand side we have an irrational number, and this cannot match, and it shows that our original assumption of root 11 plus root 17 is a rational number is wrong. We move to the next question. Show that there is no positive integer n for which root n minus 1 plus root n plus 1 is rational. So we proceed in a similar way to the previous question. That is, we assume that for some positive integer n, root n minus 1 plus root n plus 1 is a rational number. Then we can write this as, let a by b is equal to root n minus 1 plus root n plus 1. And what I will do, I will take square of both the side, and this particular term, if I square, it will be of the form a plus b square. So a square by b square is equal to n minus 1 plus n plus 1 plus 2 into root of n minus 1 into root of n plus 1. This is nothing but a square by b square is equal to 2n plus 2 into square root of n minus 1 into square root of n plus 1. Now what I will do is that in this particular equation we have the two terms, and for n plus 1 I will take this equation, isolate n plus 1 and substitute back in this equation. Okay, so we have our original equation, and I will take square root of n plus 1 is equal to a by b minus square root of n minus 1. Okay, so I have this equation, this I am going to substitute here. Okay, on substitution I will get a square by b square is equal to 2n plus 2 into root of n minus 1, and this is going to be a by b minus root of n minus 1. And now I will expand the terms, so it is 2n plus 2a by b, the square root of n minus 1 minus 2 into n minus 1. Now this will come to be 2a by b square root of n minus 1 plus 2, and this side is a square by b square. How? Because this 2n and this 2n will get cancelled out. Now I will isolate root n minus 1 from this equation. A square by b square minus 2 is equal to 2a by b root of n minus 1, or a square by 2b square by 2ab is equal to root of n minus 1. Thus we have found an expression for root n minus 1 in terms of a and b. Now that I have found an expression for root n minus 1 in terms of a and b, I can substitute this in this equation and I can get an expression for root n plus 1. Let me do that. I will get root n plus 1 is equal to a by b minus a square minus 2b square by 2ab, and I will put this in bracket. Okay, this will come to be a by b minus a square plus 2b square by 2ab, or a square plus 2b square by 2ab. Okay, so now I have got an expression for root n plus 1 also in terms of a and b. Okay, so we have one expression for root n minus 1 and we have another expression for root n plus 1. And what we have to do in this question, we need a sum of this term and this term, and we have to check whether that is a rational number. To do this, we can analyze this particular part and this particular part. Once more, these two terms which are same as this, these are going to be definitely a rational number. Why? Because a and b are integers. But we are doubtful about these two terms. Okay. Now, when can these two rational numbers, that is these two rational numbers, be same as this? This can only happen when this one and this one are perfect square. That is, these two equations, they are going to be correct. That is, these two sides match and these two sides match, and this can only match and this is only possible if this n minus 1 and n plus 1 are perfect square. Okay, when n plus 1 and n minus 1 are perfect square, then we will be able to find a square root here and here, and that square root will be a rational number and it will match the other side of the equation. Okay, now what we have to see is that when can n minus 1 and n plus 1 become a perfect square. So how can I check that n minus 1 and n plus 1 for some positive integer n will always become a perfect square? So let us check what will be the gap between these two numbers. N plus 1 minus n minus 1, you will get 2. Okay, that is a gap of 2 exists between n plus 1 and n minus 1 for any positive integer n, or it means that with a gap of 2 we have to find two perfect square. Once more I will repeat, we have to find two numbers within a gap of 2 and it has to be a perfect square. Okay, now let us check that what kind of numbers will form a perfect square and what are the gaps between any two potential perfect squares. So what is a list of positive integers? They are simply 1, 2, 3, 4, 5, 6 and so on. And what will be the squares of all these numbers? It will be again 1, 4, 9, 16, 25, 36 and so on. So let us check what is the gap between two consecutive perfect squares. Okay, these are nothing but perfect squares, right? So let us check what are the gap between two consecutive perfect squares. So 4 minus 1 is going to be 3, 9 minus 4 is going to be 5, 16 minus 9 it's going to be 7, 25 minus 16 it's going to be 9, 36 minus 25 it's going to be 11, and it will continue. What we can observe here is that the gaps 3, 5, 7, it is always increasing in value, right? It is never going to decrease in value, and the smallest that we have is 3, and that comes for these two perfect square, that is 1 and 4. So for two consecutive perfect square, the least gap possible is 3. Once more, for two consecutive perfect squares or for any two perfect square, the least gap that is possible is 3. You take any other two perfect square, the gap will be always more than 3. And in this question we have to find two numbers within a gap of 2, and those two numbers has to be a perfect square. So is it possible? The overall answer is no. The conclusion is the minimum gap possible between two perfect square is 3, which is for 1 and 4, and in this problem we have to find two perfect square within a gap of 2. Okay, that we found out here. Thus there is no positive integer n for which root n minus 1 plus root n plus 1 will become a rational number. Next question is, prove that 2 minus root 3 by 5 is an irrational number given that root 3 is an irrational number. In this question it is already provided that root 3 is irrational, so we have to make use of that knowledge. So let a and b be any two integers and we are going to assume that 2 minus root 3 by 5 is equal to a by b is a rational number. So I can rearrange this as 2 minus root 3 is equal to 5a by b. I will isolate root 3. So root 3 is 2 minus 5a by b. Now it is given in the problem that root 3 is an irrational number, and on the RHS we have 2 minus 5a by b, and a and b are integers, so definitely this whole term will be a rational number. I will repeat, 2 minus 5a by b is going to be a rational number, and we also know that root 3 is a irrational number, hence this is a contradiction. Or it means that the initial assumption that we took is wrong, and 2 minus root 3 by 5 is a irrational number. Prove that for any prime positive integer p, root p is irrational. So let us consider any positive prime integer p, and let us assume that root p is a rational number. So we can write root p is equal to a by b, where a, b together form a coprime. That means a by b is in its smallest form, or there are no common factors between a and b other than 1. Let us square both the sides. Squaring both sides, we will get p is equal to a square by b square, or b square p is equal to a square, and so we can write p divides a square. Why? We have multiplication of two numbers resulting in a square. That means p is a factor of a square, or p divides a square. And if p divides a square, it also means that p divides a. So you may have a confusion how this has come. So we have a theorem that p be a prime number, and in this problem we have considered p as a prime number. It is given in the question. So let p be a prime number and a be a positive integer. If p divides a square, then p divides a. So we have used this theorem to write this part. Okay. So now I can write a is equal to p into c for some integer c. Now what I will do is that I will take a equal to pc and I will substitute here. b square p is equal to a square is equal to pc whole square is equal to p square c square, or b square is equal to p c square. And what does this mean? It means that p divides p square and p divides b. We have applied the same theorem as stated before, and now I can write b as b is equal to p into d for some integer d. So together we have one statement that p divides a, and second statement as p divides b. So together we have p divides a and p divides b. So what does this mean? This means that p is a common factor of a and b. Okay. And this is against the original assumption of a and b are coprimes. We started the problem that a and b are co-primes, right? That means there is no common factor between a and b other than 1. But through this problem, as we did, we observed that p divides a and p divides b, so p should be a common factor of a and b, and this violates our original assumption. So in nutshell, root p is irrational. If the prime factorization of a natural number n is 2 cube into 3 square into 5 square into 7, write the number of consecutive zeros in n. So we have the given number n is equal to 2 cube into 3 square into 5 square into 7, and these factors I can rearrange as 2 into 3 square into 7 into 2 into 5, I write it as whole square, okay, or n is equal to 2 into 3 square into 7 into 5 into 2, and square of it we will get 100. The value of n, that is 2 into 3 square into 7, whatever this number is going to come, this will end with some digit other than 0, and we are multiplying this whole answer with 100. That means the overall value of n will end with 2 zeros, or the number of consecutive zeros in this number n will become 2. A and b are relatively prime numbers. Then what is their HCF and LCM? And we have 4 options given. Please take a moment to go through it. So it is given in the problem that a and b are relatively prime numbers, okay. That means there is no common factor between a and b other than 1. So what will be the HCF of a and b? HCF of a and b is nothing but the highest common factor between a and b, and that is simply going to be 1, okay, because a and b are co-prime. And what about the LCM? LCM between a and b is going to be the direct multiplication of the two numbers a and b. Now when you look at the options, you will see that option C matches this answer. Let us move to the next question. If a and b are prime numbers, then what is their HCF and LCM? Again, please take a moment to go through the options. So how do we solve this? It is very simple. It is as same as the previous problem. Here a and b are prime numbers. That means there are no common factors between a and b, or the HCF of a and b is simply going to be the 1, and LCM of a and b is going to be the direct multiplication. So the answer is as same as in the previous problem. HCF is 1, LCM is AB, and it is going to be option third. If P, Q are prime positive integers, prove that root P plus root Q is an irrational number. So let us write root P plus root Q equal to A by B, and AB form a coprime, okay. What I will do here is I will square both sides, okay, and I will write P plus Q plus 2 into root P into root Q equal to A square by B square. Rearranging, I will get P plus Q minus A square by B square is equal to minus 2 into root P into root Q. Now what I will do is that I will isolate root P from this equation and I will substitute here. I will get root P is equal to A by B minus root Q, and now I will substitute the value of root P in this equation. I will get P plus Q minus A square by B square is equal to minus 2 root Q into A by B minus root Q. I can expand this side. It will be minus 2a by b into root q plus 2q, and on this side I have p plus q minus a square by b square. Now I will rearrange the terms. I will get p minus q minus a square by b square is equal to minus 2a by b into root q. Further, if I rearrange, I will get root q is equal to pb minus qb minus a square divided by minus 2a into b. Sorry, it will become b square. So it is given in the problem that p and q are prime integers, or square root of q is going to be an irrational number. Fine. And on this side we have an expression in terms of a, b, p and q, and all these are integers, that is a, b, p, q are integers, and together this forms a rational number. And this is not possible, right? We cannot have an irrational equating to a rational number. Once more, square root of a prime number is always going to be irrational, and on the RHS we have a fraction using integers a, b, p and q, that is this term, and this RHS is always going to be rational, so we have a mismatch here. And in this problem, one more approach to think is that we need not do all this exercise. We have root p plus root q as the question asked, and we can straight away say that p and q are prime integers, so definitely square root of a prime number is always going to be irrational, and we know that sum of any two positive irrational numbers, in this case root p plus root q, will always result in a irrational number. Let p be a prime number. The quadratic equation having its factors as 0 is, so we have a prime number p and we also have a quadratic equation. The question is that we will have some solutions for the given quadratic equation, and those solutions has to be the factors of the prime number. So for any prime number, what are its factors? Factors of any prime number p, it will be always number 1 and the number itself, right? So how can we write the quadratic equation? We have to write a quadratic equation whose solutions will be same as these two numbers, and these two numbers are factors of the prime number p. So I can write this as x minus p into x minus 1 is equal to 0. So expanding, you will get x square minus px minus x plus p is equal to 0, or x square minus p plus 1 into x plus p is equal to 0, and this will be same as option B.